Yep.
today? Yes, cool. That's cool stuff. Please take it away.
All right. So we're going to keep on going and talk about like how we're actually going to do science with the things that we talked about yesterday. So this should bring it home nicely. Okay, so all right, so what we have now is basically like using like neural networks and like CNNs, we have a universal function approximator. So that's like a very powerful fitting function. And so this is it's super powerful because we can take like any function and approximate it with whatever accuracy we like. So I was asked over the break, like if there are applications of machine learning where like somebody is using machine learning and they shouldn't use machine learning. And the answer is like, well, you know, machine learning is basically a fitting function. So if you don't need a fitting function, you should not use one. You should use like the real function. This is useful when there's a good reason to be using a fitting function. Like your real function could be too slow to evaluate. And so having a fitting function is useful because it's faster. Or if your real function is not expressive enough to capture what you want to be doing with it, then you might want to use a more flexible function to fit like their data with more flexibility. So these are examples where it would be useful. But like, of course, I'm not saying that we should all just go all the way machine learning. If it's not useful, like you shouldn't be using it because it's a fitting function, there's a loss to using a fitting function. Okay, but it is a very powerful tool. So I'm just gonna give an example with like strong lensing to like give an example of what we can do in terms of science with this. So in strong lensing, you're looking at like background galaxies. Well, in galaxy-galaxy lensing, you have like a background source whose light rays have been deflected by the gravity of some intervening structure. And so because of that, you see like a distorted image of the background galaxies, like looking at the flame of a candle through the foot of a wine glass, like what I'm showing here. So you have like the flame of the candle that's like wrapping around the foot of the wine glass. And so this is like an inverse problem like this, where like your data is the pixels of the distorted image. And what you want to do is simultaneously like reconstruct the undistorted image of the flame of the background source, so like the galaxy, and reconstruct the mass distribution in the foot of the wine glass. So these are the parameters you're trying to reconstruct. So that's like the vector contains your data. You have your lens and your source parameters. And then depending on your parameterization, it could be linear or nonlinear parameters. And then you have a noise of vector of like noise that gets added to that. So this is like traditionally an extremely expensive and painful problem to solve, to go from the data to the background source, because it's nonlinear and it's non-convex. And if you run an MCMC, it's going to converge to the wrong minimum because it's a multimodal, and you're never going to end up sampling like the place you want to be sampling. So it's like super difficult. I have personally spent 2 million CPU hours trying to analyze one of those lenses and a whole year of my life. And so this is something I will not do again. So it's like, it's very long. And so now we can just, instead of having to like solve this really hard inverse problem, we can just put the image through like a neural network and just have it like give us the parameters, say, that describe the distribution of mass in the foot of the wine glass with really good accuracy. So this is like the first time that I did almost 10 years ago that we did deep learning. And so we trained the CNN to estimate like the mass parameters in the foot of the wine glass, so basically like the mass, the position, the ellipticity, the angle of like the foot of the wine glass. And it does a pretty good job. And then the main point is that this is like 10 million times faster than like traditional methods. And so instead of like, this was for, like these numbers were for like, if we scale to like the number of lenses we're going to be expecting to discover with LSST, instead of taking like 1,400 years of a person's time to analyze like the LSST lenses, it would take, half an hour on a laptop. So that's like really a game changer in this case. But the problem is that this is just a point estimate, right? Like every one of those points, this is like the true value on the y-axis versus the ground truth on the x-axis. So for every lens, I have a point. But that's not what we want to see if we want to be doing science with those lenses. Like what we want to see is more something like that. We want to see the posterior with uncertainties. Like if we want to be using machine learning as the statistical model of the data, then we want to have uncertainties and be able to quantify them. And that's how we learn things and we do science. So we need to understand what are the sources of uncertainties when we have machine learning as part of our pipeline, analysis pipeline. And so this is my game plan for this lecture. I'm going to talk about multiple different methods to do that. So first, I'm going to talk about Bayesian neural networks and approximate Bayesian neural networks. And then I'm going to talk about simulation-based inference. And then I'm going to talk about NREs, neural ratio estimators very, very briefly. All right, so let's get started. So to be able to quantify like uncertainties in estimators that neural networks give us, we need to understand what are the sources of uncertainty. So in machine learning language, there's like two names for those sources of uncertainty. There's the aleatoric uncertainty. So that's the uncertainty that comes from like the data itself. Like there is noise in my CCD, and so there is noise in my data, and that I just cannot get rid of it. There's no amount of training that's going to make that noise go away. It's just a property of the problem that I have. And then there's the epistemic uncertainty, and that comes from like the neural network itself. Like it comes from the model. So this is in principle, I could train it away. So that's like, if my architecture is not complex enough, I'm going to have error. If like my neural network is not trained enough or trained well enough, then there's going to be error. It's an estimation. So it's a source of error that comes from like the model that I'm training, the model that I have to do my inference. And all right, so let's talk about BNNs and approximate BNNs. So the idea behind like a Bayesian neural network is that we want to capture those two sources of uncertainty. So the first thing that we're going to do is that instead of having the neural network predict like a point estimate for the quantity I want, I'm going to have it predict the distribution of that parameter. So I'm going to have the neural network estimate its own uncertainties. So like I had a neural network like that, like this is like the graph that we did yesterday that was predicting like some parameters. It could be like the mass of my lens in the foot of my wine glass, but instead of having just a point estimate, I'm going to have it predict the parameters of a distribution. Like, for example, if I assume that my posterior is a Gaussian, I could have the neural network predict the mean of the Gaussian distribution and its standard deviation. And so basically, and then I have access to like a distribution from a single image, right? And then I have to change my loss function. Instead of training just for the mean squared error, I'm going to have to like give it a way to train this. And so what I do is that instead of having the mean squared error, I'm just going to have the log likelihood as the loss for my neural network. And in this case, because this is the log likelihood of like a Gaussian distribution, I just need a label for the true value of the parameter. I don't need to have a label for the uncertainty, the sigma. The network's implicitly going to learn the right sigma. Because if I make the uncertainty too wide, it's going to be very good for this term and the loss, but then this term is going to really penalize it a lot. But if I make the uncertainties too small, then this term is going to become small, like the determinant of the covariance matrix is going to make it too small, but it's going to be very small, but then this guy is going to become very big. So it's going to learn just the right balance of uncertainty to really, truly represent the distribution that I'm trying to learn. So that's great, but it doesn't tell me, like, basically what's the error on the parameters that I'm training themselves. Like, this is still completely deterministic. Like, every time I'm showing, like this, it's the same image to the neural network, I'm going to get the same thing out. Like, this is a completely deterministic network. It doesn't tell me what's the error on this value of mu and this value of sigma that my neural network predicted. So I want to capture that too. And that comes from the uncertainty that I have on the weights here that I'm training. And so what I want to do ideally is be able to capture that source of uncertainty, like all the parameters, all the W values that I trained, they have some uncertainty. And I want to be able to capture that and marginalize over it. So in a regular neural network, all the weights have fixed deterministic values. Sorry, like I was pointing at the wrong thing, but all the weights here, like on the arrows, I was totally pointing at the wrong thing, sorry. All the weights have fixed deterministic values. So that means every time I put the same thing in, I get the same thing out. In a Bayesian neural networks, we replace those fixed deterministic values by probability distributions. So, and then what we want to do, so every weight has its own probability distribution, and then we want to learn that distribution and then marginalize over it. So every time that we do like a forward pass, we would put the same thing in the neural network and then sample those distributions for every one of the weights. And so every time that I do that, I would get a different output. And then I'm going to collect that, basically Monte Carlo over those distributions, collect the output, and that's going to implicitly marginalize like over the weights. Does that make sense? Yeah, okay. All right. So yeah, so basically, like if I assume that like my noise is, my observational noise and my like data is Gaussian, this is going to be the log probability for the weights themselves. So when I want to know what's the probability of an output given some input and some training data, that's going to be proportional to like basically having marginalized over that distribution for the weights that I learned. So, and then that's what I just said. We can basically like use an MCMC to sample the likelihood, like this likelihood here, to marginalize over the weights of the distribution. Okay, But that's going to be like really expensive to do for a very deep neural network, right? Because then I have to run an MCMC, like treating every weight of my neural network as a parameter in that MCMC. So if you think about like, I don't know who's running MCMCs here? Like a lot of people, right? What's the largest dimensionality of number of parameters you have sampled? 30? It's a few tens, right? Like anybody beats 30? 40, okay, yeah, 40. Anybody's done 100? It gets painful, like really seriously painful at 100. Like you could maybe like try to push it at a couple hundred, but like it really doesn't go much more than that. So like deep neural networks, they have millions of weights. So we're not going to be doing that over like modern kind of neural network architectures. So this is really limited to kind of like pretty small neural networks if we want to be able to do that. So it has to be like networks, like we're not going to be doing even like, you know, AlexNet that like was published in 2012. I think it had 8 million parameters. Like even networks for like more than 10 years ago, they had a couple million parameters. So this is just not gonna do it at all. If we want to like get all the benefit of the expressivity of those really deep neural networks, we're not going to be able to do that here. We can do simple neural networks without very complicated neural networks. So, but this is, you know, it's something that you can do. There's papers that are being published with very small neural networks that have very few like layers or a few activations. Sometimes they're very physically motivated. So it's something that can be done. But it's not going to scale to like very high dimensional problems like neural networks. So instead of that, what we can do is we can say, okay, we're not going to learn like the very free-form distribution that we have no idea what it is. We're going to use variational inference to solve this problem and still be able to do that with deep networks. So instead of trying to learn this free-form like distribution that I have no idea what it is, I'm going to replace it by some parametric distribution that has some form with parameters that I know what they are, and then I'm going to try to learn the distribution of those parameters instead, okay, using variational inference. So basically, the process of learning is trying to find the parameters of the Q that makes the Q distributions as close as possible to the P distributions that are like the true free-form distributions. So, and we can do that using variational inference. So basically, this is like the true thing that we want to do. But then instead of, if we manage to like, if we replace this guy by this Q distribution, then instead we can just do the marginalization using the Q distribution and never have to touch the P distribution. So then the question is like, how do you find a Q that's as close as possible to the P? And this is done by minimizing the KL divergence between the two distributions. Have you guys heard about KL divergences? Okay, so it's like a metric. It's not a metric because it's not symmetric, but it's kind of like a metric. So it defines a distance between distributions. But it's not a distance because it's not symmetric. So that's why it's called a divergence. Okay? So basically, it measures the difference in entropy from the fact that like the Q is not the same distribution as the P. So like, I don't know, I can write it down, I guess. We talked about the cross entropy yesterday, right? I'm going to write formulas about entropy again. So we talked about the cross entropy, right? So we have that like the cross entropy, this is my distribution. I have like some true distribution P, and then, so that's the, and then this is like the wrong distribution, like that. Here, do you guys remember that? So if I had like the true distribution, this would not have been Q, this would have been P, okay? But then there's extra entropy from the fact that I have the wrong distribution, really. So reality is still given me by like the real P, but then I'm trying to evaluate the entropy with the wrong distribution. So I get the cross entropy. So the KL divergence is the difference between the extra entropy that I have because I have the wrong distribution and the true distribution, the true entropy I would have had I had the real distribution. So I subtract the x, p, x log px. Okay, and if the q becomes the p, then this goes to 0. So basically, the KL divergence, I try to drive it to 0, and if I drive it to 0, then I have learned the correct distribution as the q here. Does that make sense? Okay. So that's kind of like the intuition. So it's a way of defining a distance between this, but it's not a distance because it's not symmetric, but it's a way of measuring how different two distributions are. Okay. So then we have to do like a bit of math. So the KL divergence is basically, this is really hard to evaluate. So instead of evaluating this, what I'm going to do is I'm going to put the Q here. This is called the reverse KL divergence, because I flipped the two distributions, but it's still going to go to 0 if I manage to learn the right Q. The reason why I do that is because the P is really, I don't know what the P is, but I still want to evaluate this. So I have to use some matrix to make the P go away, but has still something I can drive to 0. So I'm going to try to find a bound on this and drive that bound to something very small to make this go to 0. Because if I upper bound it, then I can minimize the other thing that I know is an upper bound on this, and that's going to go to 0. Because this I know that it's strictly positive. Okay, so I'm going to use Bayes' theorem. So these are actually like expectation values. So this is, I don't know if you're familiar with like, but in stats and in like computer science, really often people write this as expectation values. So it's like x sampled from Q, and then this is the expectation of log Q, and this is minus expectation value x sampled from Q log P. Works like that. So this is the same way of writing. Are you familiar with that notation? Well, now you are. Okay, so this is how I wrote it down. So the expectation, I mean, like expectation means like expectation. So it's the integral under like the x sampled from the Q distribution. So basically, so this is exactly what I've written down there. Like what is written here is what's written down on the board. Okay, same thing. And then, so what I'm going to do is I'm going to use Bayes' theorem on the thing that I don't know how to write down, the P, the probability of the weights given my training set. So I just use Bayes' theorem to write it as the joint, and then as basically like the joint like that. And so I'm going to have this, and then I'm going to use Bayes' theorem again to split. I'm going to rewrite this guy. What did I write down? Yeah, so I'm going to rewrite this guy and use Bayes' theorem again to split it into those 3 terms like this. And because the training set and the weights are independent, then I can split it like this, because the x is like the input of the neural network. So the input of the neural network doesn't depend on the weights. So I can split it like this. And then I'm going to repackage it, again, using Bayes' theorem like this, to have this term here that I can now evaluate, this term here that I can evaluate, this term, which is my prior on my weight, and this term here. Okay, and so basically what's going to happen here is that this can be written as a KL divergence. So between this distribution and this distribution here. So these are KL over basically my priors that I have. And this is the log likelihood of my labels given my my output of my network, and then given the training set and the weights that I have. And this is another term that's like the evidence of my data. And so with this is basically exactly what the elbow is, this term. And then there's this guy that's like a strictly positive. And so because of that, so this is in machine learning, this is called the evidence lower bound here. It's like something that captures this guy and the KL divergence that's there. And then it has, if I drop the strictly positive term, then this means that this is going to be larger than this. And so I can flip it around by taking the negative on the other side. And because this guy is strictly positive, when I take the negative, it's going to be like bounded by 0 and the elbow. So if I maximize the elbow, then I'm going to end up minimizing the KL divergence. So that's basically the idea of what's going on. So I managed to just bounce. So okay, so I know there was a lot of math. You can just take your time and look at it at home, but if you really care. But the point is that I went from like a distribution that I did not know to evaluate, how to evaluate. Like I have no idea how to evaluate this, and I wrote it in terms of all things that I can actually evaluate. So those 2 terms, I can actually evaluate them. And so, all the part that I don't know how to evaluate, I know that it's just written in a way that's positive, and I can just throw it out. And so I managed to bound my thing. Yes.
Could you explain why that's strictly positive again, that first line?
It's strictly positive because if you have the wrong distribution here, your entropy is going to be bigger than with the true distribution. That's kind of conceptually why. Yes.
So I wonder what like Q is look like it's some kind of Gaussian?
I didn't
or-
say what it is. It's just a parametric distribution. So you can think of it as like a Gaussian, right? So it's gonna have two parameters. It's gonna have, trying to like say it's gonna have a mean and a variance. You could think of it like that. But then the real distribution could be anything. It doesn't even have to be like written down as like, analytic functions. It could be anything. But I'm just trying to find the parameters that make the Q as close as possible to the P. That's not parametric. So that's basically what it is. So obviously, like my choice of Q is going to be very important, and that's the whole problem with these methods. Okay, so I did not tell you how to choose the Q in a smart way, but that's kind of the idea. So now we have, if I give you a Q with like its parameters, if you find those parameters that maximize the elbow or like minimize the negative elbow, which is what I've written on here, which is basically like the log likelihood, then you can, so this is your objective now. So you can find the weights that minimize this, and you're going to be done. So you know that you're going to have weights that make your Q as close as possible to the P without ever having needed to know P, which is kind of magic. But it's great. So we have an objective that we can work with now. So basically, during training, we try to find the parameters of the Q by optimizing the elbow. OK, so what we had before is we had this untractable thing that we had to marginalize over with the P distribution that was a distribution of the probability distribution for the weights that we didn't know how to evaluate. Now we've replaced it by Q, and we have a way to train for what the Q is. So we still need to do that integral at inference time. We still need to marginalize over the weights, but now we know what the Qs are, right? So the way that we Monte Carlo over this distribution is by presenting the neural network multiple times with the same image, every time sampling different realizations out of the Q distribution to have different weights. So every time it's going to be like a different neural network that I'm passing my input through. And then I just collect the outputs, and that's going to form a distribution, basically. And if I have my network, if my distribution, my output distribution is like a mean and a variance, I'm going to have a distribution over means and variances. And those are independent sources of error, so I can just compound them the way that you would normally. OK, so I didn't tell you what the Q is. So actually, Gaussian is not the best choice. For a neural network, the simplest, the sort of the choice that makes everything work out really nicely is to use a Bernoulli distribution. So what a Bernoulli distribution is either 0 with some probability like P, or some value W with some probability 1 minus P. So it's like either 0 or some value. And the parameter of the distribution is that value. And the reason why this makes it very simple is that if I use this as my variational distribution, like my Q distribution, then it's like using dropout in my neural network. And dropout is this function that's already implemented in all the machine learning libraries. So I basically don't need to code anything extra. I can just use all the functions that have already been coded for something completely different for just regularization purposes, and just use that to basically capture the uncertainty of my neural network. And so do you guys know what dropout? I guess I didn't talk about it yesterday. So dropout is basically like the weight of the neural network is either 0 or some value with some probability P, which is exactly the dropout rate P, which is what's like, is exactly a Bernoulli distribution. So when you turn on dropout and you feed an example inside your neural network, the weights are going to be either 0 or their value. So effectively, you're going to have different architectures every time that you're putting in all. So it's like you're chopping up the nodes, basically. So the weights that are 0, you're just cutting those nodes. And so the effective architecture of your network is going to be changing, depending on what's your realization of dropout. So that's kind of like what's going on. So it's a way to regularize, because it's effectively making your neural network smaller than what it actually is. But it's also a way that you can capture your uncertainties. OK, and the reason why it makes things simple, that I didn't say, is that this was our learning objective that we had before. But with dropout with the Bernoulli distribution as the Q distribution, then optimizing this, it can actually be simplified a lot. And it turns out that it's just like learning the log likelihood, which is exactly what we were doing before. So it's exactly the function that I wrote down at the beginning. With dropout, that's the only thing we have to optimize, because this boils down to this, and the KL divergence, because that boils down to being the L2, an L2 regularization on the values of the weights, which is perfect, because we can now evaluate this very easily. OK, so how do we get uncertainties on the neural network? We place dropout before every weight layer that we have. So that's like replacing our weights by the distribution Q. Then we train with dropout on by optimizing the log likelihood like this. And then at test time, we keep dropout on, which is not what you would do normally when you're doing dropout. You would just turn it off to sample, to not sample. But then what we want to do is we want to sample. So we keep it on, and then we do Monte Carlo dropout, which means that we sample, like we feed the same input multiple times to the network, every time with a different realizations of the weights. So a different realization is the weight on or off, and we collect all the outputs. And then from every Gaussian output, we collect one sample by sampling that distribution. And these are our final samples that we collect at the end. So now we've compounded the two sources of uncertainty, the aleatoric uncertainty and the epistemic uncertainty. Does that make sense? Kind of? OK. So this is how we marginalize over the weights of the network. So this is an example of how to do it. I've already posted the slides. So if you're curious, we can look at it. So basically, this is just going to be putting dropout before every weight layers. And the loss is going to be the log likelihood. And then we can train it. And so I haven't spent a lot of time trying to train it. But this is like the training data that's noisy. And then there's like some ground truth that's like the blue line. And so I can sample and get the uncertainty over my line. So this is like at test time. Basically, I have uncertainties over my prediction that correspond to like how uncertain I am. So I could make it better, but I just didn't train it very much. You can train it and play with it if you like. OK, so this is an example on the problem that I actually tried hard to solve. So this is the prediction for the 1 sigma prediction for the some parameters magnification for this strongly lensed galaxy. So we see that they're distributed like the way that they should. And then we can get like the marginals over the different lens parameters that we have for this lens. And we can compare with the posterior samples, like the posterior uncertainties we would get by actually sampling the posterior. So the black line is sampling the posterior, and the red lines are the uncertainties that come from the Bayesian neural network. And the red posteriors are wider because they have the additional uncertainty that comes from the neural network itself. So it's as we should expect. Does that make sense? But we can see that so the uncertainty is wider, but if your science is not critically depending on having your posterior as precise as possible, this is multiple million times faster. So for example, if you want to do background source science, the uncertainty of the lens itself is not the main critical thing that you need. You just need to have a lens model, and so that would totally be good enough to do background source science. OK. All right, so this sounds like really great. So one of the pros of this method is that it's amortized. You guys know what amortized means? OK, so if I want to NC sample my lenses, like I have my first lens I'm trying to sample. So I try to get it at the right place. I optimize it. I find my place where I think my posterior line is. And then I start my sampling. And I produce a lot of simulations to get samples, right? Like you have to do hundreds of thousands, millions of like proposal simulations if you want to do like a chain, and then you need to think your chain, and then you're done, and you have your samples, and then you publish and you go home. Now you want to analyze your second lens. All of those simulations that you ran for the first one are completely useless for the second. You need to start like from scratch, right? So you're not using any of the simulations you did for your first inference. You didn't learn anything to analyze the next lens. And so there's a lot of wasted compute in that. And this method, you need to do a lot of simulations initially to build your training set. But then once you're trained, you're done. Like you've learned all the possible posteriors for all possible lenses. So you're only sampling at inference time, you're just doing feed-forward passes for your neural network and collecting the output. You don't need to run any more simulations. So what it means amortized is that you did all like the training once, and then you can infer any possible data that you would like without needing to do any fine-tuning to your training or any more training. So that's what it means. Does that make sense? So Monte Carlo, like MCMC sampling is not amortized, but this is. OK. So it's very fast because we need to do like a few hundred forward passes at test time to collect our samples. So it's still like pretty fast. And then another thing that's really great is that it's going to marginalize implicitly over all the nuisance parameter that I don't want to explicitly model. So for example, like in my lens model that I showed before, it was just the parameters of the lensing galaxy. I didn't have any source parameters. Those are implicitly marginalized over. I didn't need to model them. They were just ignored in my inference process. And then if I get, Okay, so like like I showed, like the posterior is a bit wider than it should be. But like if I actually really care about precision, what I could do is I could do importance sampling on my final samples to reweigh them so that I get like an actual like very precise posterior, and then they would be like, this would be like an honest to God posterior. So if I have good coverage that I actually like cover the mode of interest with, like in this case it did, then I can do importance sampling and get the honest to God posterior. So this is really good. All right, what are the caveats? Because there are very important caveats. So the first thing that you should know is that I use a very, very simple distribution for my Q distribution, right? Like this is a Bernoulli distribution. And so there is no guarantee that this distribution is flexible enough to capture the true P distribution that I'm trying to model with it. Like my KL divergence is going to make it as close as possible to the P distribution, but if I don't have the flexibility, it's just not going to be good enough. So in the lensing problem, you can get good coverage, and it does work because it's a simple, well, it's a simple problem. But in other problems, it just doesn't work. Like you just don't have the required flexibility to get good coverage and certainty of your like uncertainties, and so you just get biased estimators. So for example, if you're trying to like remove the foreground, the dust foreground from the CMB to get CMB mapped, it's bias. You cannot get good coverage over those things. Or if you're trying to remove noise from like some spectrometer because you're doing IR spectroscopy and you want to measure spectra of like exoplanets or something because you're doing transit spectroscopy, you cannot get good coverage with a Bayesian neural network, an approximate Bayesian neural network. And the thing is that you're not going to know that your variational distribution is not flexible enough to get you close enough to the P distribution. There's no guarantee, and there's no way of knowing it if you don't have access to your ground truth. So because of that, it makes it taste a bit bad, like because you never know if you have no guarantee that you have like the right posterior, and you don't know if you're biased or not. So it's very risky to be doing very serious science with it. So it's very fast. It can be a good way of getting a sense for your uncertainties. But for doing science where it's absolutely really important to get accurate posterior estimation, like if you're doing cosmology, for example, then I wouldn't trust something like this. Does that make sense? Yeah? Do you guys have questions? Yes.
Is that connected to like what you have in parentheses there where it says provided one can actually write the posterior?
So in the case that you cannot write it, then you don't.
Well, you cannot do importance sampling because to do importance sampling, you need to get the density, right? So if you cannot get the density, if you cannot write down the density, then you cannot do importance sampling. Or if like all your samples are biased, like so the mode of your posterior is like where my coffee cup is, and all your samples are here. Good luck doing importance sampling because you're gonna have no sample at the coffee cup.
Right.
Right?
Okay.
So you need to have samples like, where the real mode of your posterior is. So like if like the true posterior is my coffee cup and like my samples are here, then and I can write down the density here, then I'm golden. Like I'm good. This is gonna work. But like there's caveats.
I see. Okay, thank you.
Okay. Sorry, that's good? Okay, perfect. But it can still be like very useful to do something like if you want to do some like so you have a trigger thing that you want to do because you want so it's not like you're not doing like critical like precision science, then it can be very useful to do something like this because it's very fast and it's very easy to train. Okay. All right, but this brings us, if we want to do like precision science, this brings us to simulation-based inference. Okay. So the idea behind simulation-based inference, it actually comes from something that's pretty old. That like, have you guys heard about ABC, approximate Bayesian computation? Yeah. Okay. So it's kind of based on around like the same thing. So let's say that I have like a one-dimensional like data. So my data is just like one value. It's a scalar. Okay. And I have some parameter that I'm trying to infer from that data. And I have a really good simulator. So I have a simulator that can simulate like the physical process that generates that data and the noise, like everything about it. I can simulate exactly like what the data is. So I can just sample from my prior that parameter, pass it through my simulator, and then plot what the predicted data should be. So I can do this. I have 1 point, I have a bunch of points. I can do it a bunch of times. And I'm going to start populating this like histogram here. Well, it's not a histogram, this plot here. Okay, so then when I have some, like, I can actually, like, using this, I can just Monte Carlo the data. So basically, all the sims that match exactly my observation, like exactly with the noise and everything, these are samples from my true posterior, like this. So if I have an observation here, and I get all the points that like exactly fall on my data, because I'm simulating my noise as well. Then, and I collect those in a distribution. These are posterior samples, like it's called like Monte Carlo in your data. So, but then like, if my data is not like a scalar, if it's like an image, then it's gonna be really hard to like have like samples that exactly match your data, like with the noise and everything. So typically people say, okay, what I'm gonna do is I'm gonna calculate a compressed statistics of my data that's gonna be informative about what I care about. Like in like CMB physics people, typically they use the power spectrum because they know it's a sufficient statistics. But then you could do like other compressions of your data that make it lower dimensional, that make it easier to land on the right thing. So you can just use the summary statistics of the data as opposed to the data itself. That's going to make it much easier to land at the right place. But then it's still going to be like very low probability that you're going to end up on exactly the thing that you did observe. So what ABC is basically you're going to define, on top of this compressed statistics, you're going to define some like epsilon parameter that's a threshold around your observation where you're going to accept the simulations. So you're going to make like the region of acceptance a bit wider, and you're going to collect those as like OK samples from the posterior. So it's going to make your posterior a bit fatter, but then it's still going to be guaranteed to be unbiased. So that's what ABC is. But then there's this like hyperparameter epsilon that you need to tune. If you make it too small, you accept no simulation. When you get too big, you lose all sensitivity. So it's kind of like a fine balance between this. And this is not amortized because you need to start doing your simulations to collect them every time that you're like you have a new observation. But this is like, the good thing about this is that this is a legit way of getting posterior samples. Like this is serious, like this is rigorous statistics. So this is going to give me an unbiased like estimate of my posterior. It's just that if I don't have a sufficient statistics, it's not going to be like as precise as it could be. So I'm going to look precision, but I'm never going to be biased. That's the thing. And then if I have an epsilon that's too big, it's also going to be less precise, but it's not going to give me anything biased. So that's like the good thing. All right. So now, so how can machine learning help this? So basically, we have like this like collection of points. So what we could do is we could say, well, I can just use machine learning to learn the density in that joint space, right? I can just like, I have contours here in this like 2D space now, but like it could be higher dimensional, where I can say, okay, this represents a distribution. And the distribution that it represents is the joint distribution of my observation, or like the compressed statistics of my observation and my parameters that I care about. So I could try to learn this joint distribution with some machine learning method. And then once I've learned it, then for any observation, I can just cut through like that learned density now, as opposed to like the samples themselves, and get samples out of that cut, and that's going to be my posterior. So that's like the idea behind simulation-based inference. So now in practice, the way that it's done is that we can either, so we learn like, instead of learning the joint, we want to learn a conditional model on basically like so if I give it like basically, it's going to learn the whole distribution, but it's going to be conditioned on observation, because that's what I want to know. I want to know like my posterior is conditioned on the data that I got. So I'm going to give it a condition, and then that model is going to spit out like the posterior that corresponds to it, basically the cut through that density. So if my observation was up there, it would be a different condition, and it would be like my posterior would be up here. If it was down here, my posterior would be down here, because it's like conditioned on the observation. It gives me the cut through that joint distribution that I want, which is exactly what the distribution is. So that's called neural posterior observation. Neural posterior neural posterior estimation. That's what it's called. So NSPE, or another algorithm that people use a lot is sequential neural posterior estimation, SNP. So that's not amortized anymore. It just means that once you kind of get an idea of where your posterior is going to land, you start generating more simulations around there to get a better looking, like nicer posterior. So that's like, there's a package that does it for you. It's like great. It's called SBI. And okay, so that's, you can learn basically horizontal cuts like that to directly get your posterior, because horizontal cuts are the posterior. But you can also learn like vertical cuts. So get a conditional model that learns basically the distribution for a given cut at a different parameter, and that's the likelihood. So you can learn a model, you can train a model to give you like the cut through the joint at a given parameter, and that's like estimating your likelihood. And so that's why it's called neural likelihood estimation, or sequential neural likelihood estimation. And so both ways are ways that you can get your posterior. So once you have trained a model to do that, then you need to run an MCMC, but like this is extremely fast because it's a neural network. So it just runs like within 1 second and you're done. So this is like really, really fast. The advantage of doing it like this with NLE is that if you want to change your prior after, you can just change your prior because it just goes into the second stage of sampling like the neural network. So you can, if you have different priors for different observations, it's still amortized because all the hard work of training like the compressed statistics and then getting like the density estimation is done. You don't need to touch that again. Okay, so basically the idea here, why this is such a big deal, is that this is rigorous, like a statistical framework that's guaranteed to give you unbiased posteriors. So what we can do is that we can use the power of deep learning to do the feature extraction. So basically to learn the compressed statistics. So we can learn a super deep neural network and learn something that's like really complex that's going to give you like some information that's going to be really informative about the parameter that you care about from your data. And even if that thing is wrong or has some error or is biased, we don't care because we use this as the compressed statistics, and this process of learning the joint distribution is going to correct for that bias, and it's going to give you unbiased posterior estimation with the correct uncertainty. And the worst thing that can happen is that your compressed statistic is not very informative, and then in that case, you're just going to have broader posteriors. You're never going to be biased within that framework. That's just a statistical guarantee. The only way this can be biased is if you do a bad job at estimating this distribution here, but this is much lower dimensional, typically because you've compressed in you have done a lot of compression, and so this is a really easy model. This is typically like very easy. So this is basically like, it allows us to use like the power of neural networks, and we're still fully Bayesian. So it's like kind of getting the best of both worlds. So that's why there's a lot of hype around likelihood-free inference or simulation-based inference. It's also called implicit likelihood inference because the likelihood is like hidden here, but we never needed to write it down explicitly. All right, and then one really good compression of parameters that we can get is an estimation of the parameter itself, because that's going to have a lot of like information about the parameter. So let's say that I have a strongly lensed galaxy, and then I care about the Einstein radius, so like the amount of mass that I have in the lensing galaxy. I can train a CNN to predict the Einstein radius and use that as my compressed statistics. And then on the x-axis here, I would have the ground truth. So here, this is going to be like predicted Einstein radius from the neural network. This is true Einstein radius. So it's going to look something that's really close like to a diagonal line. And then when I do my estimation, it's going to give me what's the uncertainty that I have on that parameter. Does that make sense? Yeah? OK. So I didn't tell you like how to do that density estimation. So there's a bunch of things that you can do. You can just like do very simple methods like kernel density estimation, but that's not going to be very precise. You can do some Gaussian mixture model. So there's a package with PyDelphi that allows you to do that. Or you can do more modern like packages, use normalizing flows to do it. And so SBI is a really good package to do that. So you can use masked autoregressive flows. I think that's what most people use because they work really well. Or glow flows, they also can work. So yeah. So this is the same notebook that I put yesterday that allows you to play with those different ways of doing likelihood-free inference. So first you do it with just actually sampling, and then it's a toy problem. And then you can do it with ABC, and then NLE, and then NPE. So, and then you're just filling the blank to get to sample a nice posterior. And then this one is like actual astrophysics examples. It's the same thing, but with astrophysical examples. So there's an example on gravitational waves, and there's an example on strong lensing. So you can estimate parameters with likelihood-free inference using those notebooks. So, yep, that's it for simulation-based inference. Do you guys have questions? Yeah? I'm going to quickly, I'm not done. I'm going to talk very quickly about NREs as well, but I have like 2 minutes of NREs.
So I guess the SPI really depends on how the simulations are distributed in the parameter space, and right? Because
How informative is your compressed statistics, you mean?
no, like how the simulators
Yeah, you need to have a good simulator. Like that's oh yeah, that's right. I have my list of pros and cons. Yes, you need a good simulator.
Okay, and then like so I think like how the simulations are distributed in the parameter space is like prior?
That's your prior, exactly.
Okay, and then how can you get a like, I don't know, like neutral prior to the specific science you want to, I don't know, achieve or something?
Yeah, that's the big problem with those methods. So the big problem is that if your prior is misspecified, then you're going to be biased. And if your forward model is wrong, then it's going to be biased as well. So these are like the two main problems with this. There's also another problem is that it's limited to low dimensional posteriors because you need to learn this density in this joint space. And density estimators, typically the ones that give you good conditional densities, they're limited to low dimensional spaces. So you can do a few hundreds, maybe a couple of thousands, but like you cannot do millions of dimensions. So you cannot do directly inference on like an image or a volume. So you have to have some compressed statistics and then do the inference in the space of the compressed statistics. Yeah, we should take a break, I think.
Take a 10-minute break.
Thank you, thank you. Okay, a little break. Please, if you haven't signed those waivers, if you're at all thinking of coming tomorrow morning, please sign there outside. If you have